At the top of the screen is a picture of a nuclear fusion reactor, and nuclear fusion reactors use large toroids as a method for containing a strong uniform magnetic field. So they often refer to these as a Tokamak reactor, and here's a view inside of the central portion of the reactor. It's a large toroid, and magnetic field lines travel around the toroid and are contained entirely within this ring. So here's a simpler picture of a toroid. In this case, there's a lot of space in between the windings, but in general, the windings are much more tightly packed, just like they are in a solenoid. So think of a toroid as a donut-shaped solenoid. So if we want to find what the magnetic field is inside of the toroid, we're going to use, once again, Ampere's law. So let's state Ampere's law. The integral of B dot ds is equal to mu naught times the amount of current enclosed by your Amperian loop. In this case, an Amperian loop is already shown. We're going to choose an Amperian loop in the form of a circle concentric with the toroid. Now we should not only picture our loop, but we should have a picture of what the magnetic field lines look like. So as we just stated, the magnetic field of a toroid really does lie exclusively inside of the toroid. So the magnetic field lines, like all magnetic field lines, wrap around on themselves. So there's one magnetic field line, and there's another one, and there's some magnetic field lines inside of that toroid, but the magnetic field here in the center of the donut is 0, and out here, and not approximately 0. There really is no magnetic field at all in any place other than the interior of the toroid. So this becomes perhaps the simplest derivation of all. The magnetic field is just as strong on this segment of my Amperian loop as it is this segment. So the B comes out of the integral sign. We don't need to bother with any vector notation or dot product because the magnetic field is at all points parallel to the ds. So we just have B times the integral of ds is equal to mu naught times, now there's 1, 2, 3, 4 on this one because there's so much space between the windings. We could probably actually count the number of windings in this picture, but in a typical toroid, the windings would be packed so closely together you wouldn't be able to count them. You would just say that there's n number of windings, and on every winding, this current I passes once through my Amperian loop, comes back around, passes twice, 3 times, 4 times. So it's n times that current I that's flowing through the full toroid. So the integral of ds just gives us the total path of our chosen Amperian loop, which would be equal to, we can call this capital R, and we'll measure that to the center of the toroid. So we can say there's a distance A to the interior and B to the exterior. But if the width or the thickness T is much, much smaller than R, then we can neglect the difference between A and B and just approximate by measuring to the middle. And so the distance for our Amperian loop is 2 pi r. So B times 2 pi r equals mu naught Ni. So B is equal to mu naught Ni over 2 pi r. So I'd encourage you to take some time and review all the notes you've taken so you can come up with a summary of expressions for all the different equations we have for calculating magnetic field for different arrangements of current flowing in wires. And try to decipher in what cases, in what shape of a current carrying wire are we forced to use the brute force method known as law of Biot-Savart, right? When do we have to lean on the idea that dB is equal to mu naught over 4 pi I ds cross r hat divided by r squared? And when can we use the simpler approach that the integral of B dot ds is equal to mu naught times I enclosed?